Hi, my name is Yossi Cohen, and I'll present a paper by Professor Felner, Dr. Roni, and me about solving the longest simple path problem with heuristic search. The longest simple path problem is a classic computer science problem when we need to find a path from starting point to an endpoint. It's an NP-hard problem. For instance, this is the solution for this problem. You probably ask, why should anyone try to find this kind of path? Then there are some real-world applications for this problem, such as VLSI design, error corrections, and robot patrolling. There are some very basic differences between the longest simple path problem and the more familiar shortest path problem. For instance, if our agent is in the middle of this graph, in shortest path we didn't really care how it got there. But in the longest simple path, we can see that it's influenced our valid operator. For instance, if we moved in this path, we can't go up. But if we moved in this path, we can go up. Generally, I can say that the search space is much bigger in this problem, but for more details, you should read the paper. There are also minor changes to the search algorithms that need to be done in order to solve this problem. For instance, A-star need to change the open list to have maximal node comes first, and the branch and bound need to prune if the best candidate is larger than the F value. Another important thing is that better heuristics are heuristics that tightly upper bounds the remaining path. So it's obviously that shortest path heuristics just won't work in this domain. Previous works on this domain offered mainly two heuristics. One is the reachable heuristics, when we can count the vertices that are reachable from the search frontier and from the goal. Another one is the biconnected components heuristics. When we run a biconnected component algorithm, the output of this algorithm is a block cut tree. You can see the block cut tree of this graph here. And we count in this heuristic only the vertices that appear on the branch between the search frontier and the goal. In this example, you can see that if you want to go from here to there, this block is not relevant. We are offering a new heuristic named the alternate steps heuristics. Here you can see a problem, a solution, and this checkerboard. You can see that we are traveling from white position to black position, white, black, and so on and so forth. This alternation implies that the delta between the white count and the black count must be one maximum. And you can see also here that we have three obstacles on white position, and the solution didn't step on three black spots. Please notice that these heuristics can be applied on top of reachable and on top of biconnected component heuristics. The alternate step heuristic can be used on top of reachable heuristic and BCC heuristic. This example shows that we can do this separately. If we run the alternate step counting over each and every block of the block cut tree, the BCC output, you can see that we can get lower value. This is because if we run it over reachable, for instance, we're counting the entire graph. But if we run it separately, this white spot will implies one less black spot, and this black spot will imply one less white spot. And this is give us lower H value, which is good. In the paper, we're also offering two brand new pruning methods for the LSP problem. Investigating the search tree, we found out that there are many search nodes that are very similar, so why not prune them? The first pruning method is called basic symmetry detection. In this pruning method, when we are generating a node, we're looking at the open list to see if there is another node that covers the same area. If we have one and it have also the same frontier, we can ignore it. To do that efficiently, we're using a hash function on the covered area, and when we're generating a node, we're comparing all the nodes that have the same hash value. The second pruning method, called Reachable dominance detection. You can see in this example two nodes, one in the open list and generated node. Both share the same frontier, but we can see that the generated node visited in more places, so we can prune the one in the open list and replace it by this one. Sadly, we didn't find a way to do that efficiently, so we are comparing the entire open list for every generated node. This is cost time, and we will see that in the experiment's result. Another example for search node that will be pruned by the reachable dominance detection is this one. In this example, we will prune this one because here we traveled more, we share the same frontier location, and this reachable area contains this reachable area. So actually, this node is better. On our first experiment, we used the solver to solve 360 grid maps. We limited the solver to 10 minutes, and this table summarizes all the instances that were solved by all the permutations. You can see here the expanded nodes summary. Here is the runtime summary. Here is the search algorithm. Here is the pruning. NP means no pruning, basic symmetry detection, and reachable dominance detection. As for heuristics, R mean reachable heuristics, alt mean alternate space heuristics, BCC means biconnected component heuristics, and here is the separate alternate steps heuristic. You can see that reachable dominance detection prune more than basic symmetry detection, but it costs more time. Here we can see, here you can see the time. You can see that for this experiment, Bertrand bound was faster than A star for the same pruning and heuristic combination. And you can also see that we have order for the heuristics results and for the pruning results. The second experiment was on grid maps with rooms. You can see here how the pruning affects for each algorithm, and also here. Notice that reachable dominance detection prune a lot, but it is not efficient on runtime. You can also see that the efficiency of the different algorithms here. The third experiment was on two domains, live grids and uniform road. It was the longest. We limited the solver to 1 hour, and here we wanted to see the number of solved instances for the 4 algorithms. We compare here A star to DFBnB, and we compare no pruning at all and reachable heuristics, the worst heuristic, to our best heuristic by connected component with separate alternate steps, and the fastest pruning method, the basic symmetry detection. You can see that branch and bound solve more than A star or equal to A star, and you can see that our methods help to solve more instances. And now for the conclusion, we offered new heuristics for the longest simple path problem and search space pruning techniques. We showed that our techniques reduce the number of search nodes. We also showed the effectiveness of the heuristics and the pruning methods. As for future work, we showed that BSD is faster than RDD, but RDD have strongest pruning ability. So how we can make RDD run faster? The source code for this work is publicly available in the GitHub. Thanks for listening.